Good evening, everybody, and welcome to the IET Somerset and West Wiltshire Local Network, our second venture into the world of webinars. My name is Peter Schreck, and along with Oliver Holt and Andrea Lund, we are your hosts for tonight. How did we get here? Well, during 2019, I was looking for ideas to encourage interest in STEM subjects and especially computers. Fortunately, 2019 was the 50th anniversary of the first moon landing on the 20th of July, 1969 at 2017 GMT. It was an event that virtually stopped most of the world whilst we all watched it live on television, the broadcast of this historical moment. Anyway, I got to hear about Robert Willis, our lecturer for this evening, on the Apollo guidance computer used on the moon mission, which Robert gave back in October 2019 for the National Museum of Computing. And if you've not heard about this museum, I would strongly recommend, if you like this subject matter, to go and have a look at their webpage. They do a number of things. They're obviously shut at present because of COVID, but they still do it. They're doing some virtual events, but more importantly, they're doing STEM outreach and virtual teaching packages for schools, which you can take part in. So it now gives me great pleasure to introduce our speaker for this evening, Robert Willis, who works as an engineer for Cisco in Harpenden, and he writes software for routers at the core of the internet, which require a degree of software resilience, which you don't find in most of the products we have in our houses, our homes, should I say. Robert, in his spare time, has a keen interest in the history of computing, and particularly enjoys talking about computers, as you'll find out tonight, and the people involved, as well as the technical side of things. So a nice mix of history, people, and technical. Robert has been fascinated by the Apollo guidance computer for 10 years, and he's still learning new things about this extraordinary machine. So tonight, Robert will describe to us the final stages of a lunar descent, and especially the last seconds when it appears that the mission might be aborted. And with that, I welcome you to listen to Robert. Thank you.
July the 20th, 1969. Neil Armstrong and Buzz Aldrin were in the lunar module, 40,000 feet above the moon's surface and descending rapidly. All seemed to be going well when suddenly the onboard computer indicated a 12:02 program alarm and the computer restarted. Neil Armstrong, as ever, remained cool, calm and collected and radioed Houston with just a hint of urgency in his voice, asking for a status on the 12:02 alarm. 3 nail-biting seconds later, Houston gave Armstrong the go to continue. Suddenly, another program alarm happened, and another, and another, and another. The last one just 2,000 feet above the moon's surface. There could not be a worse time in the flight to be having computer problems. At the time, the press gleefully reported how Armstrong seized manual control from a crippled and failing guidance computer and managed to single-handedly and heroically land the spacecraft with program alarms flashing all around him. Nothing could be further from the truth. Neil Armstrong was a brilliant pilot, but the Apollo guidance computer worked flawlessly in this mission and every other mission that it flew. And this was thanks to pioneering hardware and software design principles that were used to make the system robust against any failure, and which form the foundation of all sorts of robust and reliable software that we use today. In this talk, I'm going to introduce you to the Apollo guidance computer. And then I'm going to show you step by step how the computer landed the spacecraft on the moon. Then I'll talk about some of those design principles that were used to make the system robust. And finally, we'll jump back into the cockpit, go over the events of the Apollo 11 landing, and I'll show you how the Apollo guidance computer played its part in saving the mission. I shan't repeat Peter's excellent introduction about who I am. Suffice to say, I'm absolutely fascinated by this computer, and I hope that by the end of this talk, you will be too. And I'd like to say a special thank you to the IET. So since I've been aged 10 years old, I went to talks organised by the IEE, as it was back then, and subsequently the IET, and I've been a keen reader of ENT magazine. And by going to these talks, the IET really nurtured a lifelong love of electronics and software engineering inside me, and I'm very grateful for that. And it's really nice today to return the favour and give a talk. So as a way of saying thank you, I've put an extra bonus section into this talk that I've never presented before. So time permitting, hopefully I'll be able to add that in. And just one other piece of admin, I know that we've all been staring at screens a lot. So if you need to take a break to make a cup of tea or whatever, the best section to do that is the third section in green when I talk about the mission software. And just another reminder, if you have questions, put them into the Q&A box in the Zoom chat and we can get them answered at the end of the talk. Okay, great. So let me introduce you to this amazing machine. There it is on the slide. It was designed at the MIT Instrumentation Laboratory, and it was responsible for almost all of the guidance, navigation, and control on the Apollo missions. The same hardware, but running different software, was used on the command module, so that's the mothership, and the lunar module, that was the spaceship that landed on the moon. So each mission flew two identical versions of the hardware. The computer weighed only 32 kilograms, consumed only 55 watts, and occupied only 1 cubic foot of space. Even today, I think these numbers are extraordinary, but back in the 1960s, I just have no idea how they managed to get the computer that small. And it ran at between 50 and 100,000 instructions per second. But as you'll see later, you can do a lot with 100,000 instructions per second. The computer was built completely from scratch from one type of logic gate, the 3-input NOR gate. And as I'm sure everyone on this call knows, you can construct any digital circuit you like out of NOR gates. And about 5,500 of these NOR gates made up the final computer. These gates were on integrated circuits. You had 2 gates per IC, so in total about 3,000 ICs made up the computer. And these ICs weren't soldered together, they were welded together to form modules like this one. And if you look carefully, you can see pins running along the top of that module. 26 of those modules plugged into a backplane using those pins, and that connected everything together to form the final computer. I'm very happy to answer more questions about the hardware in the Q&A at the end. There's another picture of the tray with some modules inserted, and there's a picture of the backplane, and each of those little blue wires you can see is connecting the pins of the modules together. The memory was very, very limited. The computer had only 2,000 words of RAM. And on the slide there, you can see those little ferrous rings. Each of those rings stores 1 bit of data. And then the grid of wires is used to address the data and to read and write the values. The ROM was even weirder. You can see on the slide those copper wires going through rings, and roughly speaking, if a wire went through a ring, that was a 1, and if it didn't, that was a 0. So the software was literally woven into the fixed memory to form the ROM. Here's one of my favorite pictures from the Apollo program. This is an engineer at Raytheon, and she effectively has a binary listing of the program in front of her, and she's weaving those thin copper wires through the rings to form the final ROM that will go onto the spaceship. The computer was very featureful, especially given it was made up of only 5,500 gates. It had a real-time clock, interrupts, parity checking, and extensive I/O connectivity. But it also had some quirks. It used a 15-bit word size. It used ones complement for integers, which meant you could have 2 different values of 0. It had no floating point support, but actually that's okay because you just use scaled integers, and in many ways that's better. And rather than lots of special instructions, it used lots of special memory locations that did various special things. As we've already seen, the memory was very, very limited. It had no stack and a very bizarre and awkward instruction set that would be very unfamiliar to a modern day programmer. In terms of I/O, the DSKY was the main way that the astronauts interacted with the guidance computer. And you can see that there's a numerical display on the top right, some indicator lamps on the top left, and a keypad at the bottom. It used a verb-noun format for commands. And there were many other human interface devices present, such as an 8-ball, indicator lamps, and hand controllers. The computer was able to send data back to Houston and receive data from Houston over the radio. And of course, if you're a computer controlling a spacecraft, you have some very exotic and exciting I/O devices like thrusters and a massive rocket engine. And I'll show you all of these I/O devices being used later on in the talk. Okay, great. So that's my introduction to the guidance computer. Now for one of the main sections. So I'm going to explain to you how the computer landed the astronauts on the moon. First, we're going to need a spaceship. So here's our spaceship. And the first thing we need is a big rocket engine. And we'll use that rocket engine to give us lots of thrust, and we'll use that thrust to slow ourselves down and come gently out of orbit and touch down on the surface. We also need to be able to steer, and that functionality is provided by the RCS thrusters. The main source of data for the guidance computer is the IMU. There's also a radar, which is able to measure the height of the spaceship above the moon's surface. Next, and very importantly, is the window, and I'll have lots to say about the window later on. And finally, sitting in the middle, tying everything together, sits the Apollo guidance computer. It receives data from the IMU and the landing radar and all sorts of other devices, and it controls the big rocket engine and the RCS thrusters and various other systems. I just want to talk about a couple of these more unusual devices. So first, the RCS thrusters. On the left-hand side of the slide, you can see that there's on 4 corners of the spacecraft, there are these quads of RCS thrusters. And on the right-hand side is one of those quads. And you can see that the thrusters are mounted at right angles. Now the computer can give little squirts of thrust through any of those thrusters. And by doing that, it can steer the spaceship in any direction in 3D space. So that's how the thrusters give you steering. The other device you may not have seen is the IMU. The IMU consisted of 3 concentric rings that could rotate freely inside each other. And then right in the middle of the IMU was the stable member. The stable member has 3 gyroscopes on it mounted at right angles, and that keeps the stable member completely rigid in space, no matter how the spacecraft rotates. And by having sensors on those 3 concentric rings, the IMU could tell you which way the spacecraft was pointing relative to the completely fixed stable member, and also which way it was accelerating. And from that data, the computer could integrate the velocity and position of the spacecraft. Okay, before I get to my mini demo, I need to condense about 100 hours of NASA training into 2 minutes and describe to you the physics of how you land on the moon. So to set the scene for you, we're coming into the mission at the point where the spacecraft is in the descent orbit. Now, this is a really misleading name because the descent orbit doesn't actually take you down to the surface. The spacecraft could quite happily whiz around that descent orbit forever and ever. To land on the moon, we need to do a series of maneuvers that take us out of the descent orbit and down onto the surface of the moon. Those maneuvers are the difficult bit of the landing, and those maneuvers is what I'm going to talk about today. So let's zoom in on that red part of the trajectory. The landing comes in 3 phases. The first phase is P63, the braking phase. The aim of P63 is to slow the spacecraft down. At the start of P63, the spacecraft is going really fast and it's really high. And throughout P63, we fire the big rocket engine out in front of us, and that slows us down and takes us out of orbit. So that by the time we're at the end of P63, we're just 8,000 feet above the surface and we're going a lot more slowly. The next phase is P64, the approach phase. The aim of P64 is for the astronauts and the computer to work together to fine-tune the landing site. However, at the start of P64, the astronauts are sort of on their back looking out towards space. So the first thing that happens is this pitch-over maneuver, which moves the spacecraft more vertical, and that gives the astronauts good forward visibility to where they'll be landing. So throughout P64, the astronauts and the computer work together to fine-tune the landing site. And then when they're above the landing site, we enter P66, the final phase. The aim of P66 is to touch down nice and gently, perfectly vertically, and without any side-to-side movement. So that's the 3 phases of landing. P63, the braking phase, where we slow down and lose most of our height. P64, the approach phase, where the astronauts and the computer work together to fine-tune the landing site. And P66, the final phase, where we want to touch down in nice and gently and not crash the spaceship. Okay, so that's all you need to know about how you land on the moon. Now I'd like to give you a demo as best as I can about the computer being used. Now, there's lots of details here. Don't worry too much about the details. I just want to show you how awesome the computer was at doing this particular task. So just sit back, relax, and enjoy the flight. So let's rewind the clock. We're in the descent orbit and it's about 10 minutes before we need to start doing those landing maneuvers to take us down to the surface. And the first thing the astronauts need to do is load the landing software. So to do that, on the diski, they type in verb 37, which means please load this program. And they then enter the program number, which is 63. And the computer responds by loading program 63. And one of the pieces of information the computer displays is verb 6, noun 61. And verb 6, noun 61 means I have some information about the landing to tell you. Now the computer has been programmed in with the landing site and the computer has calculated exactly what time it needs to light the rocket engine to land at that place. So the most important number there is that 600, which means 10 seconds before ignition. Sorry, pardon me, 10 minutes before ignition. Okay, let's wind forward the clock. It's now 100 seconds before ignition. The computer has an important message for the astronauts. So it illuminates the key release light on the top left of the diski. To view the message, the astronauts press the key release button, and the computer shows the message. And the message is verb 50, noun 18. Now, what does this mean? Well, verb 50, noun 18 means I'm asking for permission to maneuver the spacecraft. If you remember, at the start of P63, we need the spaceship to be on its back with the rocket engine pointing out in front of us. And the computer is asking permission to do that. So the astronauts are happy, they press the proceed key on the disk key, and that authorizes the computer to do that maneuver. So let me show you that happening. Here we are, the spaceship is in the descent orbit. We've authorized the computer to do that maneuver. So it steers the spacecraft so that we're in the correct orientation for the start of P63. Next, the computer gives a little jolt of thrust through some of the thrusters, and that's used to settle the rocket fuel in the bottom of the fuel tanks so that that big rocket engine will ignite cleanly first time. So they really did think of everything. Right, the computer's got the landing site programmed in, it's put the spaceship in the correct orientation, we're now 5 seconds before ignition. And the computer flashes verb 99, noun 62. Now, every Apollo astronaut can tell you what verb 99, noun 62 means. It means, are you sure you want to land on the moon? And the astronauts have 5 seconds to calmly reach over, press the proceed key on the disk key, and secure their place in history. Right. So let me remind you, we're in the descent orbit. We're now at the exact time of ignition. The astronauts have pressed the proceed key. We're ready to go. Well, we know how this works. It comes in 3 different phases. The first phase is P63, the braking phase. And the first thing the computer does is it lights the rocket engine at a barely noticeable 10% thrust. And this is my favorite part of the whole program. What's it doing? Well, the computer is measuring to see whether that thrust causes the spaceship to rotate around on its axis. And if the computer detects a rotation, it swivels that big rocket engine so that the thrust acts perfectly through the center of gravity, and that stops the spin. So after about 30 seconds of gently firing the engine and swiveling it to line it up properly, the computer ramps up the thrust to full thrust. And full thrust here is 94%. Now, this is not just a case of fire a big rocket engine and hope for the best. Throughout the entire landing, the computer is running sophisticated guidance algorithms. And those algorithms have 2 points in mind. The first one, in green at the bottom, is the desired landing site. That's the landing site that's been programmed into the computer. The other point in blue is the projected landing site. And that's where the computer thinks it's going to land based on extrapolating the current trajectory. Throughout the entire landing, the computer's main job is to steer the spacecraft to try and move that projected landing site towards the desired landing site. Now, at the start of P63, the landing radar can't see the moon's surface, and the only source of data is the IMU. Now, the IMU is incredibly accurate, but it loses accuracy during accelerated flight. And of course, nothing says accelerated flight like having a big rocket engine lit in front of you. So the computer doesn't know exactly how high it is, and it doesn't know exactly how fast it's going. And to indicate that, it lights the altitude and velocity lights on the disk key. As we get a bit closer to the surface, the landing radar is able to see the surface, and it can start providing really accurate height data to the guidance computer. So there's the situation we were in. Once the landing radar can see the surface, the computer clears the altitude and velocity lights. Now, the astronauts are waiting for this moment. And when it happens, they type verb 6, noun 63. And that means, please show me the discrepancy between how high you thought you were based on the inaccurate data from the IMU and how high you actually are based on the really accurate data from the landing radar. And it was common at this point in the mission to be 1,000 or 2,000 feet out. Now, when you're 40,000 feet above the surface, 1,000 feet here or there doesn't make a big difference. But as you get closer to the ground, of course, you really want to be using the most accurate data you can. So the astronauts sanity check this information, and if they're happy, they do something called incorporating. So to incorporate, they type in verb 57, which means please incorporate. And that feeds the landing radar data into those guidance algorithms. And the guidance computer will gradually correct the trajectory of the spacecraft based on this new, more accurate information. So if we step outside the spacecraft, what does that look like? Well, when the landing radar locks onto the surface and we incorporate the data, that has the effect of moving the projected landing site because the computer is in a different place to where it thought it was. And so, as always, the computer will then steer the spacecraft to try and move the projected landing site back towards the desired landing site. Towards the end of P63, the computer ramps down the thrust to 57%. Okay, great, we're halfway there. Next, we enter P64, the approach phase. Now we know what happens. The first thing that happens is the computer automatically fires the appropriate set of thrusters to do that pitch over maneuver. And then, if you remember, the main goal of P64 is for the astronauts and the computer to work together to fine-tune the landing site. How does that work? Well, the computer needs a really sophisticated way of telling the astronauts exactly where they're going to land. Something really high-tech. Yes, it's the window. The window has two apses marked on it, like this. And throughout P64, the computer shows verb 6, noun 64. And it works like this. That 5 on the top row of the disky means look 5 along the horizontal axis. And the 40 means look 40 up the vertical axis. And the astronaut looking out the window, so Armstrong in this case, he imagines a red dot at that intersection. And that red dot is the computer telling you where you're going to land. What happens if Armstrong doesn't like the look of where he's going to land? So he's got that imaginary red dot. What happens if he doesn't like the look of that landing site? Well, he can move his hand controller. If he moves his hand controller, that moves the desired landing site in the computer. And then, as always, the computer will then steer the spacecraft to try and move the projected landing site back towards that new desired landing site. It was common throughout P64 for that imaginary red dot to move around the window, particularly if Armstrong used his hand controller to actually change the place where he wanted to land. If we look inside the software, what's going on? Well, the hand controller feeds into those sophisticated guidance algorithms. The hand controller doesn't steer the spacecraft directly, instead it just changes the desired landing site. And then those guidance algorithms calculate how the spacecraft should be steered to achieve that goal. And those steering commands feed into the low-level attitude control software, which then calculates how the actual thrusters should be fired to do that steering. Okay, we're so close to the ground now. So once we're above the landing site, we need to enter P66. And roughly speaking, the way we do that is by moving that pings mode switch from auto to attitude hold. That automatically puts the computer into P66, at which point the hand controller is disconnected from the sophisticated guidance algorithms and it's connected directly to the low-level attitude control software. What does that mean? Well, it means that when Armstrong moves his hand controller, that now directly steers the spacecraft. So it's a much more direct mode of control. He's no longer changing the desired landing site, he's directly steering the spacecraft. But I want to make the point that even in P66, there is still software running in between the hand controller and the actual thrusters. So at no point is it complete manual control. There's always code running. Okay, when we're just a few feet off the ground, a big cloud of dust gets thrown up and the astronauts can no longer see outside the window. So instead, they have to look inside the cockpit. And they look at two instruments. The first one on the left is called the 8-ball, and that tells you whether the spacecraft is upright. And the other one on the right is the cross-pointer display, and that tells you whether you have any side-to-side movement. These two instruments are both controlled by the guidance computer, and they're very similar to what a pilot would use to land in the fog. Finally, once the spaceship touches the surface, a blue contact light gets illuminated. The astronauts quickly shut down the engine, breathe a big sigh of relief. And that's how you land on the moon. And that's my demonstration of the Apollo guidance computer. Now I'm just looking at the time here. So yes, I think we do have time for a quick 5-minute bonus section that I've not presented before. So we actually have a recording of Armstrong talking to mission control throughout the landing. And I thought it would be interesting to play you a little bit of that recording in the light of all the things you've just learned in the last half an hour. So let's give this a go. If you just bear with me for half a minute while I get set up. So, thanks to the Apollo Flight Journal for providing this video on YouTube. Now, this video has the astronauts talking and mission control talking. And I will talk you through everything. So all you need to do is read the text at the bottom of the screen. We're coming into the flight and the landing radar is just about to lock onto the surface. So I'm going to play the recording for about half a minute, just so you get used to hearing the different voices. So off we go.
We're going, fine. Okay, retro, go. Fido, go. Guide, go. Control, go. Telcom, go. Ginsey, go. Ecom, go. Surgeon, go. Capcom, we're go to continue PDI.
Eagle, Houston, you're a go to continue all at 4 minutes.
Get that Telcom, ED bats, go.
You're a go to
Roger,
you're a go to continue power descent. You're a go to continue power descent.
Okay, everybody, let's hang tight and look for landing radar.
Altitude 40,000.
We'll need that landing radar by 18,000.
And Eagle, Houston, we got
Roger.
data dropout. You're still looking good.
On the pings. Roger, I copy guidance. Okay.
Right, so I know there's a lot going on. Don't worry, I'll pick out the bits you need to listen out for. So the landing radar is just about to lock onto the surface, and you'll hear them talking a lot about delta H. Delta H is the discrepancy between how high the computer thought it was and how high it actually is based on data from the landing radar. So you'll hear lots of chatter about delta H.
Okay, we got data back.
Radar flight looks good.
Raj.
2,000 feet.
Raj, 2,000 foot delta H.
We got good lock on.
Let me know when he accepts it, guidance.
Roger.
Altitude lights out. LH is minus 2,900. Roger, we copy. At the Earth, radar our front window.
So the discrepancy is 2,900 feet. So that's within limits. It's all going really well. At this point, the first program alarm happens. Now read the bottom left-hand side of the video and you'll see Armstrong talk about the program alarm. So ignore everything else, just read the bottom left-hand side of the screen.
Houston, you're looking at our Delta 8.
Roger.
Looks good, flight.
Program
Looks
alarm.
good.
Is he accepting it, guidance?
The 1202.
Stand by.
1202.
Looks like it's converging.
Good radar data. Altitude now 33,500 feet.
So Armstrong has reported that first 1202 program alarm. Now keep reading the bottom left-hand side. You'll see Armstrong asking for a status on the alarm, and you'll see he gets given the go to continue.
Yeah, and the same thing we had.
Flight, retro.
Go, retro.
Throttle down, 6 plus 25. Give us a reading on the 1202 program alarm.
We're going
Roger.
that flight.
We're going that alarm?
Roger, we got you.
If
We're
it does
going
3
that
occur,
alarm.
we go.
Roger.
He's taking in a Delta H now.
Roger.
Roger.
Did you get the throttle down,
6
Capcom?
plus 25.
Roger.
Throttle down. 6 plus 25. Throttle down.
Flight Fido converging on Delta H.
Roger.
6 plus 25.
Flight control, we have velocity.
Roger.
So Armstrong asked for a status on the alarm. He was given the go to continue. Now, during that time, a second program alarm has happened. And at this point, Buzz Aldrin is frantically trying to diagnose this alarm. And he says something very important. He says it seems to happen when we have a 1668 come up. And I'll explain that later, but read the bottom left-hand side to see Buzz say that. It seems to happen when we have a 1668 come up. Bottom left-hand side.
Still go. Altitude 27,000 feet.
Same alarm, and it appears to come up when we have a 1668 up.
Roger, copy.
Okay, we'll monitor his Delta H flight.
Roger.
I think that's when it's getting it.
Okay.
So Buzz is onto something with this 1668. And in mission control, they're now thinking about what's happening, why these two program alarms happened. Now, the next thing that happens is the computer ramps down the throttle perfectly on time. And this, you can hear everyone gets really excited about this because it means the computer is still flying the spacecraft correctly. So listen for the next 20 seconds, you'll hear them talking about the throttle coming down completely on time. And this is giving them confidence that the computer is still working.
So Houston, we'll monitor your Delta
And his
H.
alarms.
Roger.
Delta H is beautiful.
Delta H is looking good now. Roger, Delta H is looking good
Okay,
now.
all flight controllers, hang tight. Should be throttling down pretty shortly.
Throttle on time. Roger,
You confirm throttle down.
Better in the simulator. Roger.
Right, so this is massive. The computer has throttled down exactly on time. So they're all thinking, yeah, it all seems to still be working. Great stuff. Now, the next thing that happens is there's lots of chatter in mission control about Noun 68. This is the thing that Buzz was talking about. So read the bottom right-hand side to see them talking about Noun 68 inside mission control.
How's it looking, guys?
Heights and things look real close.
You want him to stay out of 68?
Negative flight. I just said we'll monitor the alarms.
Okay.
Okay.
Flight control.
Altitude now 21,000 feet.
Go,
Still
guys.
looking
So
very good. 68 now well may be the problem here, and we can monitor Delta H.
Roger.
Flight Fido looking
Go,
real
Fido.
good.
Roger.
Velocity down now to 1,200
In
feet
7
per
minutes,
second.
you're looking great to us, Eagle.
Right, so they're in mission control, they're talking about Noun 68, and they're sort of thinking through what caused these two alarms, and all seems to be carrying on okay. Now, for the next 45 seconds, they start faffing around with the steerable antenna and the fuel gauges. So we're going to skip that. We're going to skip forward 45 seconds. Now, at this point, Armstrong starts thinking about the switch over to P64. And the time that happens is called T-go. So listen out for them talking about T-go, which is the time that they expect to switch over to P64.
Real good.
Roger.
Velocity 9,100 feet per second.
Estimated switch over time, please, Goose. Roger, stand by. You're looking great at 8 minutes.
Got an estimated, what's our T-go guidance?
30 seconds. Correction on that P64. velocity now
Roger,
reading
30 seconds.
760
You
feet
got
per
30
second.
seconds to P64.
Okay, we still got landing radar guidance.
Affirm.
Okay. Is
Roger.
it converged?
Oh, it's beautiful.
Is it converged?
Yes.
Okay.
Flight Fido, we're go. Look real good.
Raj, Fido.
Fido says we're go. Altitude
Eagle Houston
9,200
coming
feet.
up 830, you're looking great.
Right, at this point, the computer enters P64. And if you look out the window, you will see the pitch over happen. So let's enter P64.
Descent rate 129
Okay,
feet
they
per
got
second.
64.
We copy.
T-go's good.
Raj, T-goes, go.
We have position 2 on the LR.
Raj, position 2, all flight controllers, 20 seconds to go, no go for landing.
Eagle, you're looking great. Coming up 9 minutes.
We're now in the approach phase. Everything looking good. Altitude
Okay, all
5,200
flight
feet.
controllers, go, no go for landing. Retro.
Go.
Fido.
Go.
Guidance.
Go.
Control.
Go.
Telcom.
Go.
GNC.
Go.
Econ.
Go.
Surgeon.
Copy.
Go.
Capcom, we're go for landing.
Altitude
Eagle
4,200.
Houston, you're a go for landing. Over.
Okay, fantastic. So we've entered P64. We had 2 program alarms, but we seem to have got away with it. But suddenly the 3rd program alarm happens. You'll hear this quite clearly. Read the bottom left-hand side to see Armstrong reporting the program alarm, and then read the right-hand side to see them giving the go to continue inside mission control. So 3rd program alarm coming right up.
Roger, understand. Go for landing. 3,000 feet. Copy. Alarm. 1201. 1201. Roger, 1201.
1201 alarm.
Same type, we're go flight.
Okay, we're go.
We're go. Same type. We're go.
Okay, so the 3rd program alarm has happened and they've still given Armstrong the go to continue. At this point though, they're just 1,900 feet above the surface. Now take it from me that if I played you the next few minutes, you would hear 2 more program alarms happen in quick succession. You'd then see Armstrong enter P66 to avoid a boulder field, and there'd be no more alarms and he would touch down perfectly safely. Okay, great. So let me switch back to the presentation and I'll carry on and I'll explain those alarms to you. And let me just find my place. I do apologize. Okay, so what about those program alarms? 5 in total. Well, a 1202 alarm is very serious. It's a bit like seeing that on your guidance computer. Or if you're a bit more old school, something like that. Or worst of all, that. A 1202 was very serious and they had to very quickly decide whether it was safe to continue the landing or whether they should abort. And it was really important that they made the correct decision. Obviously, you don't want to continue if it's unsafe, but on the other hand, you don't want to abort if you don't need to. So the question of whether we abort is going to be the topic for the final 20 minutes of the talk, and then I'll take some questions. So first, I'm going to talk about the design principles that made the software robust, and then we'll jump back into the cockpit and I'll explain to you what the alarms meant and how the computer recovered. First, though, the mission software. And just a reminder, if anyone needs a quick break, now is the time to do it. So the software that landed them on the moon was called Luminary. And I hope you've seen from the demo that it was really quite sophisticated stuff. It controlled all phases of the mission. So it got the spacecraft into the descent orbit. It did the landing. That was the thing I demoed. It did the taking off, and it did the rendezvous back with the command module in orbit. And it controlled all of these devices like the thrusters and the rocket engine, the disky, the 8-ball, etc., etc. So to do all this, it ran a simple real-time operating system that they wrote from scratch. And of course, the source for Luminary is available on GitHub. And I want to talk about 6 design principles that were used to make the system robust. Now, these may seem obvious to us nowadays, but back in the 60s, it was by no means obvious that this was how you created a robust system. So number 1, use a high-level language. As I mentioned earlier, the AGC's assembly language was very primitive, the instructions were awkward to use, and this made it hard to actually program those complex guidance algorithms. Also, the 15-bit integers didn't give you enough precision for the really accurate calculations that you needed. So their solution was to write an interpreter, and that gave you a sort of virtual assembly language, a bit like Java bytecodes. And these sort of bytecodes were a lot more powerful. They gave you things like matrix and vector operations, which are really useful if you're doing physics calculations. It gave you such luxuries as being able to index into an array, and it gave you a stack for manipulating values and calling functions. It also gave you double and triple precision integers for greater accuracy. And also it meant that the same algorithm took up less memory. Remember, we only have 36,000 words of ROM to store the entire program in. So the fact that it takes up less space is really important. A key downside to the interpreter was it ran really slowly. So the final system was a hybrid between the two. The really time-critical stuff, like controlling the thrusters, was written in the low-level assembly language, and then the sophisticated guidance algorithms that ran on top that were less performance critical were written in the interpreter. Number 2, divide your system into jobs. The software was doing lots of different things in any phase of the flight. And so it was divided into jobs. For example, there was a job called readax, which read data from the IMU and integrated it to calculate the position and velocity of the spacecraft. There was a whole suite of jobs that implemented the digital autopilot that I demoed for you earlier. There was a charming job called pinball, which updated the information on the diski. And each job had a small area of memory called a core set that stored housekeeping information and local variables for the job. And there were 7 core sets available, which meant you could have 7 jobs on the go at any one time. Number 3, restart on failure. So it's a sad fact of life that all software will encounter failures. Now, I don't mean bugs where the programmer was lazy or misunderstood the specification. Those things would be caught during testing. I'm talking about 1 in a million transient conditions that you'd only hit if you were really unlucky. Now, if software has failed, it can't be trusted to recover itself. So instead you restart it. And the hope is that by restarting it, the transient condition has gone away and the system will recover. Number 4, checkpoint your good state. So restarting is great, but a sort of perennial problem of robust systems is that you lose your state, and some of that state might be really important. For example, state that tells you where you are and how fast you're going. So when your job reaches a known good state, which they called a checkpoint, you save that state for later. And after you restart, you read in your checkpoint to figure out what you should be doing. For example, if you're the readax job, you would read data from the IMU, you'd do loads of calculations, and then at the end of all of that, you'd get a new value for the position and the speed of the spacecraft. So when you get that final result, you would checkpoint it. But if you crash halfway through, you wouldn't touch your checkpoint. Number 5 of 6. Hardware monitors the software. The AGC used cooperative multitasking, and that meant that each job had to write code that would check whether there were other jobs waiting to run. And the way that that happened was every so often you would write an instruction that checked a special variable called new job. And if you saw a value in new job, then your current job had to stop running and hand control to whichever job was waiting. And the idea was that the code should be instrumented so it did this every 20 milliseconds. Now you might say, isn't this a bit rubbish? But I would come back and say that the software had a very well-defined purpose. It was all written by the same team without any evil adversaries. And regardless, cooperative multitasking was the only feasible way to implement this at the time. But what happens if a job gets into an infinite loop and never checks new job ever again? Well, in that case, the hardware intervenes. A piece of hardware called the night watchman will detect this. If it detects that new job hasn't been checked for 640 milliseconds, it will trigger a hardware restart. So the system can never hang forever. And finally, send telemetry. So the DSKY was just about good enough for the astronauts, but it did give a very limited view of the AGC's status. So to get round this, the guidance computer would periodically radio its internal state back down to Houston, and Houston would have a whole team of engineers in mission control who would stare at this telemetry data and they would make sure that the computer was working properly. So those are the design principles. Use a high-level language so that complex algorithms are easier to implement. Divide your system into jobs where each job does a different thing. If something fails, restart it. And the hope is that whatever transient condition caused the failure will have gone away and the system will recover. Checkpoint your good and important state so that after restart, you can pick up where you left off. Hardware monitors the software so the system never hangs, and send telemetry about your system back to experts who can monitor the system and make sure it's working. Okay, great. So in the final section, I want to jump back into the cockpit, give you another little demo and explain to you what happened during Apollo 11. So firstly, I've lied to you. There was actually an extra radar on the spacecraft called the rendezvous radar. This was completely useless when you were landing on the moon, but it was essential when you took off. The rendezvous radar was one of the ways that they found the command module in orbit. And the rendezvous radar, apologies, sorry, let me step back. Yes, so throughout the landing, the landing was very computationally intensive. Hopefully you kind of appreciate that from the demo, that, I mean, landing is pretty difficult. And this put an 80% load on the computer. And their rendezvous radar had a hardware bug. If you were really unlucky, you would trigger this hardware bug. And of course, on Apollo 11, they were really unlucky and they triggered this bug. And the bug caused the rendezvous radar to send a constant stream of zeros to the guidance computer. And that put an extra 15% load, roughly, on the computer because it had to deal with all of this extra pointless input. Now, I am simplifying this slightly and I can provide a bit more detail in the Q&A, but the gist of it is they were really unlucky. They triggered this hardware bug, which put an extra 15% load on the computer. However, 80 plus 15 is 95%. So although the computer was heavily loaded, it wasn't overloaded. And that meant that at the start of P63, they didn't notice that there was a problem. They didn't notice that they triggered the hardware bug because the computer was just about able to keep up with the load. So what changed? Well, what changed was Buzz Aldrin. Buzz Aldrin was clearly very excited to be getting down to the surface of the moon, as I would be. And he entered verb 16, noun 68 into the DSKY. Now, verb 16, noun 68 means please calculate some information about the landing and please constantly update the display. Now, I'm making fun of Buzz here, but actually this was a completely legitimate thing for him to do. He'd done it in training thousands of times before. He'd never had a problem with verb 16, noun 68 before. But what did this do? Well, when Buzz entered verb 16, noun 68, it started a new job that would calculate those numbers and update the DSKY, and it would keep on doing that. And that put an extra 10% load on the system. Now, at this point, we have a problem because now the system is overloaded. It's only slightly overloaded, but it is overloaded. So internally, the jobs pile up. And the computer can't quite keep up. And when it comes to scheduling the 8th job, there's a problem. There's no memory for that job. And the computer signals a 1202 alarm, which literally means out of memory. Oh dear. What does Buzz see? Well, he enters verb 16, noun 68, and he's really excited to be getting down to the surface. And then he sees 2 lights that you never want to see when you're landing on the moon. First is the program alarm light, followed rapidly by the restart light. Now, Buzz needs to diagnose this program alarm really quickly. So on the disky, he enters verb 5, now 9, which means please show me the program alarms. And the computer responds, and it says that a 1202 alarm has occurred, and the 3 is the type of restart that was used to recover. Okay, so all of these shenanigans happened, but the computer, the spaceship, kept on flying. Why was that? Well, Buzz's job got started. It put the extra load on the system, and that triggered the program alarm. And the computer recovered by restarting various jobs. And really importantly, it did not restart Buzz's 1668 job because it was considered not important enough. That removed the transient load from the system and allowed it to recover. So that's the cause and the recovery for the first program alarm. But Buzz, of course, is really annoyed. He's entered verb 16, noun 68, and all that's happened is the computer's crashed. So he leans over to the disky and he enters verb 16, noun 68 again. And the same thing happens. A new job gets started. It puts an extra 10% load on the computer, and that, coupled with the hardware bug, overloads the system. The jobs pile up. When it comes to scheduling the 8th job, there's no memory, and again, a 1202 alarm gets triggered. Once again, the computer recovers by restarting jobs. It doesn't restart Buzz's job, and the system recovers. So that's the second alarm. Now, those 2 happened quite high above the surface. What about the other 3? Were they caused by Buzz as well? Well, no, I can assure you that at that point, Buzz was sat on his hands. He was never going to enter verb 16, noun 68 again. As you heard on the recording, he realized that the alarm seemed to happen when we have a 1668 come up. Buzz didn't understand why that caused the problem, but he did correctly make that connection. So why did the other 3 program alarms happen? Well, they happened a lot later, during P64. If you remember, during P64, the computer is calculating that imaginary red dot, and the astronaut is correcting the landing site as appropriate. And these happened a lot lower, just 2,000 feet above the surface. Now, P64 is just a more computationally intensive task. And it actually just, as the baseline load on the system just increases. And so that, coupled with the hardware bug, causes the system to naturally overload itself without Buzz doing anything. But in all cases, the computer is able to recover by restarting various failed jobs, and is able to keep on flying the spaceship all the way down to the ground. But there's one final mystery. Why was it that when Armstrong seized manual control, why were there no more program alarms? Well, that's simple. Armstrong, he didn't seize manual control at all. He just entered P66. Now, he did enter P66 early, but that's because they were flying towards a boulder field and he wanted to avoid it. Now, when Armstrong entered P66, that connects the hand controller to the much lower level attitude control software. That naturally reduces the load on the system, so it's no longer overloaded. And that's why no more program alarms were seen once Armstrong entered P66. Just going back to those design principles, how did they help? Well, restart on failure. The computer recovered from the transient high load condition by restarting jobs. The fact that the system was divided into jobs meant that less important things like buzzes 1668 were not restarted, and it meant that the really critical software like the autopilot kept on running. Checkpoint your good state. So even after these restarts, the guidance routines, they knew exactly what they were doing because they could read in the information from their checkpoint, and that allowed the spacecraft to keep on flying. And finally, sending telemetry. As you saw, even diagnosing the program alarm with the DSKY was really clumsy. But because the computer was sending telemetry back to mission control, that gave them the confidence and the authority to give Armstrong the go to continue. So there we are, that's my explanation of the program alarms. As the talk comes to a close, I'd like to pick out two people. Now, there are so many people I could talk about, but I've just picked two. The first is Steve Bales. And you actually heard him on the recording. He was the one talking about Noun 68 in mission control, and he was the one who gave the go to continue. He accepted the NASA Group Achievement Award on behalf of the entire mission operations team. And this is an incredibly prestigious award within NASA. And in the words of Nixon, this is the young man when the computers seemed to be confused, and when he could have said stop, or when he could have said wait, said go. And the other person I want to talk about is Margaret Hamilton. She led the team at MIT who developed this software. And she finally received the US Presidential Medal of Freedom in 2016. That's the highest civilian award you can get in the United States. And that was for her entire career of developing techniques for creating robust software. And just to tie this into the modern day, as Peter said earlier, I work for Cisco and I write software for Cisco's really high-end routers. And these fault-tolerant techniques that were pioneered in the 60s form the foundation of the software I work on and all sorts of other software. And although it's not quite as cool as landing on the moon, I think using these techniques on networking software is really great fun. And finally, because I'm presenting to the IET, I just couldn't resist asking for a little bit of help. So I'm in the early stages of trying to build a replica of the AGC out of NOR gates using WireWrap. And this would be very similar to a prototype that they developed in the early 60s. My electronics knowledge is good, but I'm completely self-taught and I only have experience of low frequency circuits. So I would be very grateful if anyone could offer me a few hours of technical advice about 4 megahertz digital circuits using 6,000 logic gates, because I have absolutely no idea what I'm doing and things seem to go a bit weird when you cross the 1 megahertz boundary. So if anyone would be able to lend me a couple of hours of their time, I'd be very grateful. And finally, just to mention, Peter said that this Zoom is being recorded. Also, the National Museum of Computing have put together a great recording of this talk, which you can easily Google for on YouTube. And I think Peter may send a link out afterwards. And if you enjoyed my talk today, please thank me by supporting the Museum of Computing. So I hope you enjoyed the talk. With that, I think I'm going to answer some questions. Is that right?
Yeah, so thank you very much, Robert, again, for your wonderful webinar I've had this evening. I've certainly learned so much, more than I thought would possible about the Apollo guidance computer. There's much more to it than I first thought. So from myself, all of the people who've joined us, all over 460 participants, the IET Somerset and West Wiltshire local network as a whole, thank you very much for your time this evening. So yeah, we'll hand over to you for some questions. To everyone else listening, if you haven't already, please post your questions in the Q&A box on the bottom right of Zoom, if you haven't already. I see we've had quite a few repeat questions, lots of people asking about one of the missing programs. There's program 65 has come up a lot, which I'm sure is a question you've had before, Rob. But yeah, the Q&A will run until about 8:30, so that's another 20-25 minutes for most people here. You don't have to stay for it if you don't want to, but it will be included in the recording when we publish it. If your question isn't answered, we'll try and hand them over to Rob to answer offline, but do post your questions now while you can. Okay, thank you very much, and I'll see you in a few minutes. Thanks again, Rob.
Fantastic. And one of my favorite bits about giving this talk is I usually get some really great questions. So yes, what was P65? That's a very popular question. So if you remember, I talked about 3 phases, 63, 64, and 66. And in theory, the computer could actually land itself all the way down to the moon. So if it was in P64 and it got low enough, in theory, it would enter P65 and it could land itself. In reality, the astronauts quite liked to take control, and they would to take control, they would enter P66, and the astronauts would do that before the computer had a chance to enter P65. So P65 was the automatic version of the final phase, but the astronauts liked to fly that for completely legitimate reasons, so the computer never actually got to fly that. I see another question. What voltage did the logic run at? Gosh, you have stumped me there. It was something like 12 volts or possibly 24. Don't quote me on that one. It was certainly higher than, say, 5 volts. Lawrence, was there only one computer, no backup? Yes. So there was only one computer in the lunar module. Let me give a better answer to that question. There were 2 computers in the lunar module. There was the Apollo guidance computer, and that's the machine I've been talking about. And that was the sort of the real deal. So that did everything. It got it into the descent orbit. It did the landing. It did the taking off. There was a separate computer, a much simpler computer called the abort guidance computer. And if the astronauts triggered an abort, then the Apollo guidance computer that I've been talking about would be disconnected from all of the spacecraft's control systems, and the abort computer would take over instead. And the abort computer had a very simple job, which was to take this, like, regardless of how you entered the abort, it would take the spaceship up into orbit. And then at that point, Mike Collins in the command module, he would have to navigate himself to pick up his friends in the lunar module. So there was a backup computer. It was a lot simpler, intentionally so, and it was only used during an abort. Alistair, how was the computer and software tested before the mission? Yes, that is a good question. There is very little information about how the computer was tested. It's something I wish there was more material about. So on the hardware side, I mentioned that the computer was built up out of those 26 different modules that were plugged into the backplane. Each of those modules could be tested independently. And there was a special rig called the tool stack assembly, which was like a sort of expanded version of the backplane that you could a lot more easily plug modules in and out of. So you could test the modules in isolation. The computer also had a special test port, and you could, and it was like a big connector. It had like 100 pins. You could plug a special piece of test apparatus into the test port and perform integration testing of the entire hardware. And in the end, they actually flew the real space missions with the test hardware plugged into the test port, because it was actually so useful having that extra testing ability even during the flight. On the software side, this is where there really isn't very much information. They had simulators that could simulate the AGC's assembly code, and they ran lots of simulation runs of the computer doing the landing. But to the best of my knowledge, there is no source code for those simulators, and there's no source code for the simulation runs. And I really wish there was, because it would be a really valuable resource. John asked, how much redundancy is there in the LEM, in the lunar module computer system? So as I mentioned, there's only one guidance computer. There's the spare abort computer that was a lot simpler. There was very little redundancy, actually, to be honest. The computer did have parity checking in terms of accessing memory, and that parity information was wired throughout the logic. So like when you're actually adding the numbers, it would calculate the parity internally to make sure that internally there was no error. But apart from that, there was very little redundancy. John, oh, I see. I'm just getting used to how Zoom does the questions. There we are. John says, was the memory entirely core, i.e. no semiconductor memory? Yes, that's right. The memory was the 2,000 words of RAM, that was those ferrous rings, and the 36,000 words of ROM, that was the wires painstakingly threaded through the hoops. There was a proposal that programs would be loaded from tape, but they never went ahead with that. Roy asks, where did the IMU get its initial datum or reference from? I love this question. This is such a great question. So they had to do two things to line up the IMU. The first one was called a coarse alignment, and the other one was called a fine alignment, and they sort of do what they say on the tin. So the coarse alignment was getting the IMU to an approximately known position, and then the fine alignment was really fine-tuning that to a really accurate degree. There are various ways they could align the IMU. So when the spaceship was actually on the launch pad back in Houston, they could use the wobble of the Earth's orbit to actually get a reference datum for the IMU. When they were in space, they had a sextant on the spacecraft, and they could use that sextant to gather readings about where various known stars were, and that could provide a datum. Also, I think Houston, because they were tracking the spacecraft, they could also provide a datum, possibly, although the two main ones I can think of were on the launch pad using the wobble of the Earth, and in space using star sightings to line up the IMU. And they would have to every so often do particularly the fine alignment, because the IMU would, over time, it would gradually lose accuracy, and the astronauts, they liked to play a little game. So when they were lining up the IMU using the sextant in flight, they liked to see whether they could get what was called all balls, which was like a series of zeros, which meant that the IMU was perfectly aligned and there was no discrepancy. And the astronauts used to like it when they got an all balls or completely zero set of readings when they did a fine alignment. I'm just reading through to see what other questions are here. Bruce, you mentioned that the programs were stored in a hardwired core store. A diode matrix ROM would seem to be a better choice. Can you throw any light on the reasons for the designer's choice? No, I can't. I don't know why they chose core memory. They were very conservative with the hardware design. You would not believe how much they agonized about using integrated circuits, because integrated circuits in the context of spaceflight was a really new technology. And this was why one of the reasons why they built the computer out of one type of circuit, the NOR gate, rather than lots of different integrated circuits, because they really didn't trust the technology, and what they wanted was scale to make sure the hardware was reliable. For your question about why core store was used, I don't know whether it was weight or whether it was perceived to be more reliable, or whatever. I'd assume that diodes would be heavier, but I don't know. There, I sort of fudged that question, haven't I? What I do know is, so I showed the picture of the worker weaving those copper wires to form the ROM. The Apollo program employed a large number of very skilled textile workers to do that job, because as you'd expect, it was really painstaking. If you sort of kinked those copper wires, it could be game over. Just looking for another question. Phil asked, do you know how quickly the computer would restart and get going again? Meanwhile, would the controls or guidance be frozen? The restart was very quick. We're talking about a second. It took maybe a second. The guidance software would, the whole system was divided up into 2-second time slots. And the idea was that every 2 seconds, all of the guidance software had to run and calculate what to do for the next 2 seconds. And yes, there was sort of hard real-time stuff for doing the low-level thrusters, but most of the system operated in these 2-second quantized chunks. So a restart of about a second or less than that, it messed up one of those quantized chunks, but then for the next 2-second chunk, stuff would get going again. That's a great question. Do we know if single event upsets had an effect to alarms, e.g. due to radiation events? Yes. For example, if radiation caused a parity error in the memory, the computer would detect that, and that would trigger a program alarm. What's the propagation delay between the lunar module and mission control? I don't know. But if you listen to the recordings of, like the one I showed you earlier, the sense is that mission control have basically a fairly real-time view of the system's state, kind of, within a human's reaction time. So I don't think propagation delay was a big problem. Gordon asks, in comparison with modern safety critical software, how much software testing was done? So like I said earlier, there's not a huge amount of resources about the testing. It was definitely tested. It was tested a lot, but I can't quantify that. The project was very tight. There was lots of feature creep in the software. There was huge pressure at times on the development teams. We've all been there, I'm sure. Part of that pressure was because they still needed to allow time to test it, but I don't have a more precise answer than that. So Ian's also asked about how long did the computer restart take? And I said about less than a second. I know some of these are duplicates, and that's fine. Yes, and so Fred asked me a good question, which I'm just going to sort of digest because it's a long one. Yeah, okay. So people sort of get annoyed with this hardware bug. So Fred is basically asking, he's like, well, what's the deal with this hardware bug in the rendezvous radar? So the actual to understand it, I'm going to actually give you a a bit of an explanation, just a quick one. I need a slide that I can type on. Hopefully people can see that. So the AGC had a huge number of I/O devices. And it was not, if you imagine, say, each I/O device has 15 bits of precision. For example, the rendezvous radar would be, which way is it pointing? If you had like, if you had, say, 20 devices, each with 15 bits of precision, that's like 300 connections to the AGC. And that is not feasible. However, most I/O was smoothly varying. So they came up with a clever technique. Each I/O device had a plus and a minus wire going to the computer. And so when the smoothly varying quantity went up, the device would send a plus signal. And when the smoothly varying quantity went down, the device would send a negative signal. And so hopefully you can see that's a lot fewer signals for the computer to deal with. Internally, those signals would trigger two instructions, a plus increment or a minus increment. So when the computer received a plus or a minus signal, it had to load the particular counter, add or subtract 1, and then save the counter. So this was all fine. The problem with the rendezvous radar was it, and you can Google it for a better explanation, but basically the hardware bug was that the rendezvous radar's clock was not in phase with the AGC clock. And when I said you were really unlucky if you triggered it, basically the exact time that you powered on the radar determined the phase difference. Now, if you got the phase difference like really wrong, the rendezvous radar would send a stream of pluses and minuses constantly to the guidance computer. So when I said earlier it was sending a stream of zeros, it was actually sending a stream of pluses and minuses, basically moving that smoothly varying value around 0. So those pulses, that constant stream of pulses caused by the out of phase clock, was what put the extra load on the computer, because the computer had to load the counter values, update them, and then carry on processing again. In later missions, they added an item to the checklist to basically make sure the rendezvous radar was switched off. Super. Let me see what other questions I have. What was the data rate on telemetry? Oh my goodness. So the most useful number is how quickly could the computer download all of the information. It could download all of the information in 6 seconds. In terms of the actual data rate, I don't know, but you know, we're talking like 1,000 baud or something like that, you know, horrendously slow. Not least because the data was each value is transmitted 3 times with different bit masks to counteract errors in transmission. Robert Phillips, I'm sure they would have learned the verb noun codes off by heart, but how do they correspond to real words? Yeah, there was a logic. There was a certain logic to the verb noun format. So for example, verb 6 meant please show me, and then the noun was the thing you wanted to see. Verb 16 was please show me and constantly update the display. Verb 99 was something really special was about to happen, like you're about to land on the moon. So there was some logic to it. How come the myth developed and persisted that Armstrong took control? The software engineers must have been really upset. Yeah, I guess it's quite hard to explain. It's quite hard to give more detail about what actually happened. I think Armstrong's seizing manual control makes for a good story. And it's not completely untrue in the sense that the computer would have landed in a boulder field if he hadn't entered P66 early. So Armstrong was a fantastic pilot. And in this talk, I don't want to water down Armstrong's brilliance. But I guess in this presentation, I'm trying to also say how great the software and the computer was. So Alex says, how did they unluckily trigger the hardware bug? And that was because they switched it on, they switched the rendezvous radar on at just the wrong time, which meant that its clock was out of phase with the guidance computer's clock. So it sent that constant stream of pluses and minuses. How well did the computer perform on subsequent missions? They did, over time, they gradually evolved the software as they got more confidence in it. So for example, in later missions, they added a very simple terrain model of the moon into the computer, because if you imagine that the surface of the moon is bumpy and has mountains and things, so it's helpful if when you take your landing radar readings, you account for the fact that you're flying over a mountain and you sort of take that into account. So that's one example of where they enhanced the software. The software that flew on Apollo 11 had a huge amount of self-test code built into it. And as more of these features got added on later Apollo missions, they basically deleted a lot of this self-testing code and instead replaced it with these various other features. Alex says, you explained 3 of the 1202 alarms. What about the 1201 and the final 1202? So the first 2 1202 alarms were caused by the 1668 job. The 1201 and the final 2 1202s were all caused because P64 puts a much bigger load on the computer. 1202 means out of memory for a assembly language job. 1201 means out of memory for an interpreted job. So they both mean out of memory. And Simon again asked, what was a 1201? It was the same out of memory condition. It just was for an interpreted job. I'm just looking because I'm conscious we're a little short of time, so I'm just seeing if there's any other questions that are sort of unique. I'll do one more and then I think we can wrap up. So Barry Johnson's asked, he sort of said, well, what power did the computer have? I guess what computing power did the computer have? So the guidance computer is often compared with a wristwatch, and people say, well, there's more memory there's more power in your wristwatch than in the guidance computer. And this really irks me because, as you've seen, the guidance computer was amazing. It was a real-time system. It had a really special purpose. And in some sense, it wasn't the power of the computer that mattered. It was the skill with which that limited computing power was really expertly harnessed to really solve this problem in a robust way. So I think I could quite happily answer these all day, but I think it's past, so I shall stop answering questions live and hand over to the hosts.
Thank you. Right. Sorry, Oliver, do you want to say something?
I was just going to say thank you to Robert again, and thank you for everyone who asked questions. I know we had getting on for 100 questions in the end, which is great. I know we've only answered some of them so far, but hopefully a lot of them are repeated. And as we mentioned, hopefully we'll pass them on to Robert to answer offline if possible, where appropriate. So thank you again for that. I guess you've still got a couple of minutes to get those in if you really want to. But again, just on behalf of IET West Wiltshire local network and the IET as a whole, thank you, Robert, for taking so much time to answer the questions in such an in-depth way and giving us such a great insight into what it's like what the guidance computer was doing on the Apollo 11 mission. You based on the number of comments left in the chat, people really appreciated your presentation style and how much of an expert in the field you appear to be and how good at presenting it you are. So thank you very much.